Okay, so now along with our covalent bonding comes bond shapes and bond angles. So before we have to learn about all our different shapes and their angles, only within covalent bonds, we have to know what electron pair repulsion theory is. So now electron pair repulsion theory says that electrons repel each other. Okay, so if I have a lone pair of electrons, remember that's two electrons that are together from that original atom, okay, they're going to repel each other the most. So if I have an electron there and I've got that pair there, that's a lone pair. And then it is going to repel all the other electrons. And if this one is a bond pair, this is going to repel way more than if that bond pair is next to another one. So bond pairs have the least amount of repulsion because they're two different electrons from two different atoms. But lone pairs coming from the same atom have the most repulsion. So if a lone pair is sitting next to a lone pair, that's going to have the most repulsion away from each other and all the lone bond pairs. If a lone pair is sitting next to a bond pair, it's going to have a medium amount of repulsion. And if a bond pair is sitting next to a bond pair, it's going to have the least amount of repulsion with each other. So if a molecule has all bond pairs, the repulsion is going to be equal. If it has a lone pair with a bond pair, the lone pair is going to push the bond pairs closer together. And if it has two lone pairs, it's going to push even more. So that's why our angles are not always the same. And it's going to depend on how many lone pairs and how many bond pairs are in an atom to know what the angle is. And once we know what the angle is, we'll know what the shape is going to be. So if we look at these examples of our shapes and our angles. So I have carbon that's bonded to 4 hydrogens. So there is a bond pair in every single one of them. So it's carbon with 4 bonds. So there is only bond pairs in there. So if we look at that molecule, I have carbon in the middle and it has 4 bonds and they are all equidistant to each other. Okay, because remember they are in 3D. So if you have it and you look at it, I have one molecule going up, one bond in the same plane. One is coming forward towards you and then one is going back. So in 3D, it means that I have hydrogen. See, that one's going straight up. And that one is then in the same plane as that one. So this one is then coming forward, which we represent with a solid triangle. And that one is then going backwards, which we can represent with a dotted triangle. That shows our 3D structure. So now because they are all equidistant to each other, the angle is all the same. And the angle between them, so between every single one of these, is going to be 109.5 degrees. And we call this molecule tetrahedral because it's all equidistant and there are 4 of those bonds that we have there. So anytime you have 4 bond pairs, no matter what it is, it doesn't have to be carbon with hydrogen, it could be anything. If there are 4 bond pairs in there, it is always going to look this way. And this way is going to be tetrahedral and the angle 109.5. So then, if I look at the next one, now I have nitrogen with 3 bonds and 1 lone pair there. So this lone pair is going to have a much stronger repulsion, remember, than all the bond pairs. So this one is going to push these further down. and they are going to end up closer together. So you're going to have the nitrogen with its lone pair, and it's going to push the hydrogens closer together. Okay, so they're not going to be equidistant like you thought they would. So if I have that nitrogen, so remember there's no bond at the top, there's just lone pairs. So it's pushed all of them downwards because the lone pair is pushing them further away. So it means that the angle there between them becomes closer. So where there it was 109.5, now here it's only going to be 107 degrees because of the lone pair pushing them closer together. So again, you have one in the straight plane, one going backwards, and one coming forwards. So when we draw them, we can have a solid triangle, a dotted triangle, and a straight line. And now this angle we are going to call triangular pyramidal, because we've got that triangle shape, but it's also like a pyramid because obviously it's 3D, so it's standing up. And then the last one that we can look at is if I have two lone pairs. So if I have two lone pairs, those are pushing away from each other as well as pushing the bond pairs away. So two lone pairs means that those bond pairs are going to be even closer together because now we've pushed them further away. So now that angle is going to be even smaller than the others, and the angle there is going to be 104.5. And now because there's only two of them and they're pretty close together, we talk about the shape being a non-linear V shape. Okay, so now whenever you have this, you have all bond pairs. It's going to have the same angle and tetrahedral. One lone pair with three bond pairs, same angle, triangular pyramidal. And then two lone pairs with two bond pairs, 104.5, nonlinear V. Okay, so it doesn't always have to be these specific molecules with these specific atoms. Any molecule you have, if it has this arrangement with bond pairs, one lone pair, two lone pairs, these are going to be its shapes and these are going to be its angles, okay? Because they're always going to be arranged like that. So those are the standard shapes with our standard angles, okay? The exceptions to the rules that you need to learn would be these ones. So our other shapes and angles would be, so here for example, if I've got double bonds in there, so I've got double bonds and two lone pairs on each side. The two lone pairs on each side are pushing equally from each way. So from that side and that side, they're pushing equally, and the bond pairs are all in the middle. So it ends up that there, it pushes them straight. So our angle becomes 180 degrees. So if we look at it, because we have the double bonds on each side, it pushes the whole molecule into a straight line for 180 degrees, and then it becomes linear shape. So we call that molecule linear. If we look at our boron trifluoride, so now remember there's three pairs that are bonded, but it's missing one. But now the bond pairs all repel each other equally. So because they repel each other equally, the whole thing is going to be spread out equally because there's nothing that's repelling more than the other. Like with the ammonia where it had the lone pair and it pushed them further down. So now because each of them is equal and it's missing that lone pair, the molecule becomes flat. And because it's flat, so as you can see, that whole thing is completely flat in one plane, the angle between them becomes 120 degrees, because 120 plus 120 plus 120 makes 360, because this whole thing is now a flat molecule. So now because it's flat, we call it trigonal, because it's in a triangle shape, but it's all in the same plane. So it's trigonal planar, and it's 120 degrees. Then our other one, I can now have more electrons around there. So for example, my phosphorus, but it's with 1, 2, 3, 4, 5 fluorines. Okay, remember, these don't have to be phosphorus and chlorine. It could be chlorine instead of fluorine. This could be any atom in group 3, like aluminium or gallium, any of those. Okay, as long as you have this arrangement where it's missing electrons, where it has double bonds on each side, or if it has more electrons, they're all going to have the same shapes. So now this one with our 5 means there are 10 bond electrons in that middle there, 5 pairs, and they're all repelling each other equally. But the special thing about this one that we can see, okay, is that we have the same shape in the middle, if I'm holding it, as this one, okay? Because there it's all in the same plane. And in that same plane, with those 3 atoms in there, it means that that's going to be the same angle between them. So with my phosphorus, I'm going to have my 3 of them in that same shape as that, which means they're going to have the same angle. So between there, it's going to be 120 degrees. But then I have one going up and one going down. So now if you can look there, between there, that angle there is a 90-degree angle between there and between there. So the one going straight up and the one going straight down will have a different angle to those 3 that are in the middle. So there, I can say that that's 90 degrees. So this molecule, whenever you have 5 bonded atoms, it's going to have a 90-degree angle and a 120-degree angle, okay? Because if we look at its 3D arrangement, that's how it's going to look. So we have 120 degrees, 90 degrees. So because you have 2 different angles, now our name, just like there, we have triangle shape. So we call this trigonal. And then because it's now double, because there's the top and the bottom, we can say trigonal bipyramidal or pyramid. Okay, because there's an up and a down, but it's all still triangular shaped. So that's going to be our other exception. And then our last one, if I have sulfur, but now it has 1, 2, 3, 4, 5, 6 atoms around it, so it has 6 bond pairs and 12 electrons, okay, it's going to mean that if I have a molecule like this in 3D, remember, so one's going to go up, one's going to go down, but now I have 4 in the same plane. So I'm going to have my sulfur, okay, and then 2 of them are coming forward. And when those 2 are coming forward, 2 of them are going back. and then 2 in the straight plane, one going up and one going down. So now with this molecule, I can see between each of those, because there's 4 of them, it's going to be 90 degrees. And between there, it's also 90 degrees. So all the angles between every single one is going to be 90 degrees. And a shape like this, I then call octahedral. So again, it doesn't matter. It doesn't have to be sulfur with fluorine. It could be anything as long as there is 6 atoms around there. It would be octahedral. If there's 5, trigonal bipyramidal, 3 trigonal planar, and 2 pairs of double bonds, linear. Okay, so always just look at what's bonded, and then you can remember those special angles. So 180, 120, 120 and 90, and then 90. Okay, as well as your common shapes of tetrahedral, trigonal, pyramidal, and nonlinear V at 109.5, 107, and 104.5. And those are all of our different shapes that we need to learn.